All right, in this lecture, we're going to go over collisions. We're going to begin with a quick recap of conservation of momentum, and then we'll talk about collisions in 2 dimensions, inelastic collisions, and then we'll do some practice problems. All right, so let's start with conservation of momentum. So as you might remember, if we have an isolated system consisting of many particles, then the total momentum of the system is always conserved. So that means that the total momentum before a collision would be equal to the total momentum after a collision. Okay, so we're going to use this principle here when we talk about collisions in 2 dimensions as well. So momentum is a vector quantity, so when you add or subtract momentums, you need to add them as vectors. So that means you need to consider the x components and the y components. Okay, so just like adding forces that have x and y components, you would add the x components to each other and then add the y components and then recompose them as vectors. Okay, so we'll practice doing that soon. I also wanted to bring to your attention this term called inelastic collisions. So sometimes you're going to see in a question that when 2 or more objects collide, they're sticking together. So the question will tell you they collide and they stick together. So this is called inelastic collisions, and we'll see how we can treat those scenarios as well. Okay. All right, so let's start with our first practice problem. So we have a 78-kilogram man running across a frozen lake at 2.3 meters per second, and his 21-kilogram daughter runs towards him at 1.25 meters per second. If the daughter jumps into the man's arms, what is his speed just before he catches her? Okay, so let's just kind of visualize this in our head. We have a man, and let's say the man, I'll say this little dot is the man, and he's running across the frozen lake. He's going to the right, 2.3 meters per second. And then his daughter runs towards him. So his daughter is, let's say, over here, and she is running towards him at the speed of 1.25 meters per second. Okay, the daughter jumps into his arms. What is his speed just after he catches her? So now they're connected to each other. She's now in his arms, and now they're sliding or moving together. Okay, so we're going to do conservation of momentum. We're going to say P, which is the symbol for momentum, total initial equals momentum total final. Okay, momentum is a vector, so we could put vector hats here if we wanted to signify that. All right, so we have 2 different objects here. We have the momentum of the man, or the father, I'll say M for man, initial, plus the momentum of the daughter, initial, is equal to the momentum of the man and the daughter, final. But the man and the daughter are now together. So she is now in his arms, and they're sliding across the ice together. So I'm going to call this momentum of the man and daughter as though they're just one object moving together, final. So what's the formula for momentum? We have momentum is equal to mass times velocity. Whatever the direction is of the velocity, that's the same direction as the momentum. Now we're going to just assume that to the right is positive, and based on the picture that I drew, the man was moving to the right and the daughter was moving to the left. So it doesn't really matter. The question wants to know what is his speed, and so the direction doesn't really matter since speed is just a scalar quantity. So I'm just going to say to the right is positive in this question. All right, so my formula for momentum now, I have mass times the velocity of the man, initial, plus mass times velocity of the daughter, initial, is equal to mass of the man and the daughter, so I'll put them together, mass man plus mass of the daughter, times their velocity final. The 2 of them are together, so this velocity final is referring to the velocity of the man and the daughter who are now together. Okay, so we're trying to solve for this speed after he catches her, so that's this v final here. That's what we're solving for. So let's rearrange now to solve for it. So I'm going to just divide both sides by mm plus md, mass of the man plus mass of the daughter, and I get mass, this should be mass of the man, and this would be mass of the daughter. So mass of the man, velocity of the man initially, plus mass of the daughter, velocity of the daughter initially, over the total mass of the man plus the daughter is equal to V final. Okay, so let's put everything in. The mass of the man is given in the question, 78 kilograms. The velocity of the man, we're saying the man was moving to the right, so that's a positive velocity, 2.3 meters per second, plus the mass of the daughter, she is 21 kilograms. And she is moving to the left, so we're going to say that that is a negative 1.25. Okay, you could have done this question assuming that the daughter is on the left moving to the right and the man is on the right moving to the left, and reverse the two velocities. One's positive, like the opposite one would be positive and the other one would be negative, and that would be fine. In the end, you'd get the same value for your velocity, but it would be the opposite sign, and that's okay because the question is asking for the speed, so we wouldn't include the sign anyways, so the answer would still be the same. Okay, divided by the mass of the man, which is 78 kilograms, plus the mass of the daughter, which is 21 kilograms. And now I can just type this into my calculator. So I have 78 times 2.3 plus 21 times negative 1.25 all over 78 plus 21, and I get 1.55 meters per second. Okay, the question is giving all of our values with 3 significant figures. So my answer should also have 3 significant figures. Okay, so that's why I have 1.553 digits. All right, that's it. Let's do question 2. A 68 kilogram pig is riding a skateboard on a level road. Together, the skateboard and the pig have a combined mass of 77.1 kilograms and a speed of 4.1 meters per second. Then this crazy pig jumps off the skateboard with a speed of 0.6 meters per second in the same direction that they were moving. What is the speed of the skateboard immediately after the pig jumped off? Okay, so initially we've got this pig. Okay, I can't draw a pig, so I'm just going to draw it like this. And it's on the skateboard. It's really sad drawing. This is the best I could do for a pig. All right, so I have this pig on a skateboard. That's initial. And then what happens is the pig jumps off the skateboard. So the pig is now here. Okay, so it's jumped off the skateboard, so it's moving this way, which would cause the skateboard to move backwards. Okay, so let's see what happens. So we have a 68 kilogram pig riding a skateboard. Together, the skateboard and the pig have a combined mass of 77.1 kilograms. Okay, so the mass of the pig, I'll just write this out, is 68 kilograms. And then the combined mass is 77.1. So if we wanted just the mass of the skateboard, we'd have to do 77.1 minus 68 kilograms. 77.1 minus 68, which is 9.1 kilograms. Okay, so that's the mass of the skateboard. So now initially, the velocity of the pig and the skateboard together are 4.1 meters per second. But then the pig jumps off the skateboard with a speed of 0.6. So this is the velocity of the pig final is 0.6 meters per second in the same direction that they were moving. So we're going to say the direction that they were initially moving, which is to the right, is the positive direction. And so now the velocity of the pig after it jumps off is 0.6 is also positive because it's in the same direction that they were initially moving. What is the speed of the skateboard immediately after the pig jumps off? So we're looking for the speed of the skateboard final. That's our question mark. And we should expect it to be a negative value, but since the question's asking for speed, we would rewrite it as just a positive value because speed is a scalar. It doesn't have any negatives involved in there because that would tell us what direction it's going, but speed is not a vector, so we shouldn't say the direction. Okay, so let's set everything up as before. So we'd say the total momentum initially equals the total momentum final. And we have two objects, but initially the pig and the skateboard are stuck together. So we're going to treat them as they're one big object. So I'm going to say the momentum of the pig and skateboard together initially, okay, because they're moving together, so we're treating them like they're just one big object stuck together, is equal to the momentum of the pig final plus the momentum of the skateboard final. All right, so momentum again, I'll put the equation on the side, is equal to mass times velocity. So I'm going to change my equation now. So I have momentum of the pig and skateboard would be the mass. This is the mass of the pig and skateboard, so I'm going to just separate it as mass of pig plus mass of skateboard times the v initial. So that's the initial velocity that the pig was traveling with the skateboard, is equal to the mass of the pig times the velocity of the pig final plus the mass of the skateboard times the velocity of the skateboard final. Okay, so what are we looking for? We want the speed of the skateboard after the pig jumps off. So that's this value right here, Vs final. So I can rearrange my equation to solve for it. So I have Vs final is equal to MP plus MS V initial, and now I'm going to move this to the other side, minus MP VP final over all of this, which is mass of the skateboard. Okay, so I rearranged my equation, and now I'm ready to plug in all my numbers. So the speed of the skateboard final is equal to the mass of the pig, which is 68 kilograms, plus the mass of the skateboard, which is 9.1 kilograms, times the initial velocity of the pig and the skateboard together, which was 4.1 meters per second, minus the mass of the pig, again is 68, times the velocity of the pig final, which was 0.6 meters per second, all over the mass of the skateboard, which we found was 9.1 kilograms. All right, so now I'm just typing this into my calculator. I get 68 plus 9.1 times 4.1 minus 68 times 0.6 all over 9.1, and that gives me 30.3 meters per second. Okay, so the speed of my speed of my skateboard immediately after the pig jumps off is 30.3 meters per second. Well, look, I got a positive answer for my value here. So that means that my initial assumption that the skateboard was going to be moving backwards, that wasn't correct. It's still moving forward. So the pig jumps off of it, and initially they were moving at 4.1 meters per second. The pig jumps off at a certain speed, and now the skateboard is super light because it doesn't have the pig's weight on it, and it moves faster than before. Okay, so that is the velocity of the skateboard after the pig jumps off. All right. And again, if we looked at significant figures, there's 3 over here, there's 3 over here, there's 3 over here, there's 3 over here, so my answer should also have 3, so that's good. All right, moving on to question 3. A 1,000 kilogram car approaches an intersection traveling north at 20 meters per second. So I'm going to just call this car M1. So M1 is 1,000 kilograms, and it's traveling north at 20 meters per second. So that's the initial velocity of object 1. So I'm going to say V1 initial is 20 meters per second, and I'm going to put the direction in here, north. Then we have another mass, another car, so I'm going to call that one M2. And that mass is 1,200 kilograms. And the velocity of that second car initially is 22 meters per second, but this one's not going north, it is going east. Okay, so we have one car traveling north, the other car traveling east, and they collide. The two cars collide at the intersection, and they lock together. Okay, so this is an inelastic collision. They're now stuck together. Ignoring any external forces that act on the cars during the collision, what is the velocity of the cars immediately after the collision? Okay, so essentially we're saying now that the two objects, the two cars, are stuck together. And so after the collision, we're treating them like they're just one big object. So if I were to write the formula again for a conservation of momentum, I'd say the total momentum initially is equal to the total momentum final. Okay, I can put vectors on here. I don't always put them on, but they can go on there. It's just showing that they are vectors. And so I have two objects initially. I have P1 initial plus P2 initial. So these are my two objects, my two cars. And at the end, I'm going to call it momentum of 1, 2. So these are my two cars that are stuck together. Final. So what are my formulas? P is equal to mv. So I'm going to write this as m1 v1 initial plus m2 v2 initial is equal to, my two objects are stuck together, so my mass is now the mass of both of them together. Because they're stuck, I'm treating them like they're one big object. V final. Okay, so I'm looking for this V final here. But the thing is that these are vectors and they're not both moving in the same direction or opposite direction. So it's not like I can just say positive is to the right and I have positives or negatives going on here like in previous questions. Instead, I have one moving north and the other one moving east. And so when I do this question, I really have to separate the components of it so that when I'm adding these vectors, I'm adding them as when I'm adding them as vectors with their components. So let's start with one of the directions. Let's say I'm going to start with the east direction. Okay, so in this case now I'm doing the m1 v1 x component initially plus m2 v2 x component initially equals m1 plus m2 v final x. So vx final. Okay, so I'm just looking at the x components of everything. So if I were to take my first vector, v1 initial, it's 20 meters per second going north. Okay, so the x component of that, if I were to divide this into x and y components, my v1 x initial would be 0 because it doesn't have an x component. It doesn't go left or right at all. And my v1 y initial would be that 20 meters per second. And we're assuming that positive is to the right and positive is upwards for y. So those are my x and y components of my v1 initial. And for my v2 initial, again, assuming that positive is to the right and positive is upwards, I'd say v2 x initial. So this vector is 22 meters per second east. It looks like this. It's purely in the x direction. So my x component is 22 meters per second. And my y component is 0. v2y initial is 0. Because it doesn't have a y component at all. It's only going to the right, so it's purely in the x direction. So my x component's positive 22 because it's going to the right. My y component's 0 because it doesn't have a y component at all. It's only going to the right. So I can use these x values now in the equation that I wrote to the right. I'll just highlight them so that they're more obvious to us. So I'm using these values now when I fill out this equation. Okay, so I'm going to fill out this equation. I'll highlight where they're going to go in. So my v1 x initial and my v2 x initial, I'm using the values that I highlighted on the left. All right, so I have m1 v1 x initial plus m2 v2 x initial equals the two masses added together times vx final. We're trying to solve for v final, so we're going to find vx final, and then later we'll find vy final, and then we'll put them together. So let's solve for vx final first. So I'm rearranging the equation. I get m1 v1 x initial plus m2 v2 x initial over m1 plus m2. And now I can substitute all my numbers that I know. So m1 is 1,000. v1 x initial, that's the one I highlighted over here. So that's 0. Plus m2, which is 1,200, And V2 x initial is 22 over M1 plus M2. Okay, so I'm going to type this onto my calculator. The first term just becomes 0. And now I have 1200 times 22 over 1000 plus 1200, and I get 12. So this is 12 meters per second. It's the x component, and it's positive, so that means it's going to the right. So I can do the same thing now to find my Vy final. I'll do it down below. So I have Vy final. And the equation is going to be exactly the same, so I can rewrite everything if I want to, and I'll do that just to make it more clear. So it's going to look just like this equation over here, and when I rearrange it, it will look just like this, except everything that says x in it is now going to say y. But I'll rewrite it. So I have M1 V1 y initial plus M2 V2 y initial equals M1 plus M2 Vy final. And then I'll solve for this Vy final over here, and I get Vy final equals M1 V1 y initial plus M2 V2 y initial, there's lots of subscripts going on, over M1 plus M2. So now we can sub in everything we know. So M1 is 1000, V1 y initial, so I'll start to highlight those with a different color. So right here, V1 y initial is 20, and V2 y initial is 0. Okay, so those are the values that are going in here, V1 y initial and V2 y initial. That's where we're going to sub them in. Okay, so V1 y initial is 20 plus M2, which was 1200, V2 y initial, which is 0, over M1 plus M2. 1000 plus 1200. This second term over here goes to 0. And now I'm going to type this up on my calculator. 1000 times 20 over 1000 plus 1200. And I get 9.0909, and it keeps repeating. Okay. So now that's the y component of my velocity, and since it's a positive, y is going up and down, but it's positive, so it's pointing upwards. Okay, so now we know our x component is 12 meters per second to the right. Our y component is 9.09 meters per second upwards, and now we just need to put those two vectors together. So we have one vector that's going to the right and another vector that's going upwards. The one that's going to the right is 12 meters per second, and the one that's going upwards is 9.0909 meters per second. And then that means that the resultant, which goes from the beginning of the first vector to the end of the last vector, would look like this. So this is my velocity vector. Okay, so it goes in a certain direction. This is the direction that it goes in. So I can find the direction. I'll find that first. Theta, so I would say tan theta equals opposite over adjacent, and then theta equals the tan inverse of the opposite side, which is 9.0909 over the adjacent 12. And I'll type this into my calculator. Tan inverse of 9.0909 over 12, and I get 37.1 degrees. And I can also solve for v, which is my hypotenuse. So I can find the magnitude of v. So v squared equals 12 squared plus 9.09 squared using Pythagorean Theorem. And then I'll square root both sides, and I get square root of 12 squared plus 9.0909 squared. So the magnitude of v is then the square root of 12 squared plus 9.0909 squared, and that gives me 15.05. So I should probably be rounding at this point. So my question, let's see how many significant figures there are. So see here, they tell us there's really just one, and over here there's 3, and here there's 2, and here there's 3, right? So really my answer should have 3. I mean, sorry, should have only 1 because it says 1,000 here. So my answer should have 1, but I'm going to just ask for 3 for this question. So on a test, you'll be asked how many decimal places. I really should have written, let's say, 0.0 over here in the question so that it's more obvious. So here, this says 4 digits now. I just changed it. The other one, the 1200, I'll make it 0.0. So it also has 4 digits. And then the other ones have 3, so my answer should now have 3. So let's do that. We're going to pretend that question had 3, so now my answer should have 3. So it would be 15.1, because it was 05, so I rounded the 0 up to a 1, meters per second. So now when I give my velocity, I would say it's 15.1 meters per second, and the direction is this direction first, which is east. And then from there, we're going 37.1 degrees towards the north direction. So that would be my answer. Okay. Now notice in the answer that I wrote in the question up above, I wrote north 52 degrees, 52.9 degrees east, and that's really the same thing. So I could have drawn my triangle like this instead. And when I solve for theta, my opposite side would be 12, and my adjacent side would be 9.0909. And when I do tan inverse of 12 over 9.909, that would give me that angle, 52.9 degrees. So this angle here is 52.9. This angle here is 37.1. When we add them together, we get 90 degrees, and that makes sense. Right, so whether you say east 37.1 degrees north or north 52.9 degrees east, it's the same thing. So both answers are correct. All right, that was 3. Let's move on to 4. Okay. A firecracker explodes into 3 separate pieces. 2 pieces of equal mass shoot off at 28 meters per second. One traveling south, so I'll just draw a picture of this. One's traveling south, and the speed is 28.5 meters per second. And the other one is traveling west, also 28.5 meters per second. The third piece has a mass 3 times the size of the other pieces. What's the velocity of the third piece? Okay, so the mass of the first 2, they don't tell us what they are, but they do say that they're equal. So let's just say that their mass is just m for mass. And the third piece then has a mass of 3m. Okay, because momentum has to be conserved, the total momentum initially, and I'll write this out, total momentum initially is equal to the total momentum after, or final. And initially meaning before the explosion, before the firecracker explodes. And at that point, before it explodes, nothing is moving yet. So it's just all the pieces are stuck together in this firecracker. It hasn't broken off or exploded yet. So if we were to do the mass times the velocity of each of those pieces, the velocities are all 0. So this initial momentum is just 0. So we have 0 equals the total momentum after, which means after the explosion. So we have 3 different objects. 2 of them have the same mass. The third one has a mass of 3m. We're trying to figure out what the velocity is of that third object. Okay, so the velocity of the third one is going to go up in some direction like this because it is trying to balance out the other momentums. So the 3 momentums together have to add up to 0. So if you think about vectors and how they add up, they have to all have balancing x and y components. So if you looked at the x and y components of the vector I just drew, this one would balance out with this one, and this component, the y component, would balance out with that one if I drew them the right size. Okay, so I'm just going to leave it like this. So now, what are all of my momentums final? So I have m1, which is just m, times v1, which is 28.5 but it's going to the west. So I could, what I probably should do at this point, I'm going to write them all out. V1, so this is M1. So I'll write M1, V1 final, plus M2, so this one I'll say is M2, V2 final, plus M3, so this one I'll say is M3, V3 final. Okay, I'm trying to solve for this V3, but I should really decompose everything to X and Y components. So if I was going to say my V1 in the X and my V1 in my Y initially, oh no, this is final after the collision, so it's a F for final. If we're talking about this first vector over here, if we say positive is to the right, well, this one is traveling to the left, so the X component would be negative 28.5 meters per second. And the Y component, since it's only traveling to the left, it doesn't have a Y component, it would just be 0. And if we were to look at V2, so this vector going downwards, V2x and V2y, again, if we say up is positive, well, this vector is going straight down. So the X component would be 0, and the Y component would be negative 28.5. Okay, so the V3, we don't know what it is, so we're going to try to find the V3x and the V3y, and then once we have it, we'll put them together to find the total V3. Okay, so V3 as the hypotenuse. Once we have the x and y, we can find the hypotenuse. We can just add them up as vectors. All right, so I'm going to do what we did before. I'm going to separate this equation out into x and y, so I have 0 equals m1 v1x final plus m2 v2x final plus m3 v3x final. And I'm trying to solve for v3 final, so I'm going to find v3x final here. So I'm going to rearrange the equation, and I end up getting v3 final is equal to, when I bring everything to the other side, it makes it negative m1 v1x final. When I bring this to the other side of the equals, it also becomes negative m2 v2x final. And then I need to divide by this m3 over here. Divided by m3. So that's my v3 x final. So I'll put a little x there so it's more clear. v3, just the x component. All right, so let's calculate that now. v3x final is equal to negative m1. So my m1 and my m2 are the same mass, so I'm going to just say they're both just m. And my m3 is 3 times the mass, so it's 3m. So I'm going to just put in an m, v1x, which is this value, negative 28.5, minus m2, which is just m, the same mass as m1. v2x is this value, 0, over m3, which is 3 times the mass, so 3m. So what do I get here? I have 28.5 m, because the two negatives make a positive. These two cancel out, over 3m. And now my m's reduce, and I get 28.5 over 3. 28.5 divided by 3, and that gives me 9.5. My m's cancel out. All right, so I found my v3x final. Now I can do the same thing and find my v3y final. The formula is going to be exactly the same, so I'm just going to go ahead and rewrite this equation, but this time, or I'll write this equation over here without the numbers first. This time the x's are all replaced with y's. So I have negative m1 v1y final minus m2 v2y final over m3. So now we can just plug in the things that we know. m1, again from before, m1 is just m. v1y final is over here, 0. minus m2, which is also m, v2y final over here, negative 28.5 over m3, which is 3m. So now my m times my 0 becomes 0, and I'm left with the same thing as I had before. Negative m times negative 28.5 is 28.5m, and on the bottom is 3m. So I have the exact same thing as before. The m's cancel out, and I'm just left with 9.5. All right, so now we know my v3x final and my v3y final. So I can write them out. My v3x final is positive, so that means it goes to the right, 9.5. My v3y final is positive, so that means it goes up, 9.5. Okay, so that's these numbers here. And then my resultant would look like this. So this is my v3 final. Okay, so I can find the direction of it if I like first. So I could say tan theta equals opposite over adjacent, and then solve for theta is the tan inverse of the opposite side, which is 9.5, over the adjacent side, which is 9.5. And when I do that, I get tan inverse of 1, which is 45 degrees. And then I can use Pythagorean Theorem to solve for v3 final. I'll find the magnitude first, which is the square root of the other two sides squared. And I'll type that up. I get 9.5 squared plus 9.5 squared, all in a square root sign. It gives me 13.4 meters per second. So now I can say that my v3 final is equal to 13.4 meters per second, and now I have to give my direction. So let's look and see how the question was phrased. It says one's traveling south, the other one's traveling west. So when I give my direction, I'm going to give it with northeast, southwest coordinates. So I'll say it's traveling this direction, which is east, and then this angle, which we got 45 degrees, towards the north. So east 45 degrees north. Okay, so that was question 4. Let's move to question 5. Okay, a yellow ball and a red ball of equal mass are rolling towards each other. Okay, maybe we'll do a little picture. Yellow ball and red ball. Maybe I'll use some colors. So here's my yellow ball. Other one, red ball. Okay, so they're moving towards each other. The red ball is shot to the east. Oh, that's too bad because I put them in backwards. Let's fix that up. The red ball is going to the east, so the red ball should be the one that's on the left in my picture. And the yellow ball is going to the west, so that one should be the one on the right. Okay, so now I can put in my numbers. So the red ball is shot to the east at a speed of 1.9 meters per second, and the yellow ball is shot to the west at 5.1 meters per second. They do not hit head on, but they have a glancing collision. So they don't hit like from right this point to this point. They hit at some weird angle, and it deflects the yellow ball by 90 degrees so that it ends up moving north. So after this, so this is initially over here. This is before the collision. And now if we were to draw the same picture final, our yellow ball is now traveling north. So let's draw what that looks like. So this one is traveling north, and it ends up moving north at 1.34 meters per second. Okay, so let's draw that. Yellow ball traveling north. So it's going north, and it's 1.34 meters per second. And it wants to know, well, what's the velocity of the red ball going to be after the collision? So we have some other ball, it's red. We don't know which way it's going. and we want to know what is its velocity. Okay, so this is initial, and the other one, so the first one is initially, and this is final. Okay, so we don't know which direction the red ball is going to go. All right, but we notice in the question that things are not just moving left and right. They were initially, or east and west, but finally something's starting to move north, so we're going to have some angles happening. So that again means that we need to decompose everything into x and y components. So if we were going to call this one, I'll call this MR for red. And it tells us that they have the same mass, so I'm going to just say both of their masses are m. And then VR initially, okay, is 1.9 meters per second. But like I said, we're going to have to decompose things into x and y components, because even though initially they're both moving just east and west, or left and right, at the end things are starting to move in the y direction as well, so we need to start looking at components. So I'm going to write VRX initial and VRY initial. So initially the red ball is moving east, okay, so the x component is positive and it's the same value, and the y component would just be 0 because it's not moving up and down or north or south at all, so it would just be 0. And then if we looked at mass of the yellow ball, it would still just be m because it's the same mass as the red ball, and the velocity of the yellow ball initially we said was 5.1 meters per second, but it's going west. So the first one, the red one, was going east, and the second one is going west. Let's decompose that into x and y components. So we have velocity yellow x initial and velocity yellow y initial. So it's going purely west, so that means that it only has an x component, and it's negative if we say positive is to the right, which I'll say up here just to be clear. Positive is east or to the right, so my velocity of the yellow ball in the x direction initially is negative 5.1 meters per second, and it doesn't have a y component because it's only going west, it's not going north or south at all, so it'll be 0. Okay, if we look at final now, V of the yellow ball final is 1.34 meters per second, and that's north. So if we were going to find the x and y component of that, we'd say Vy, velocity of yellow ball in the x direction final, and velocity of the yellow ball in the y direction final. In the x direction it would be 0 because it's going north, and in the y direction it would just be positive 1.34 meters per second because it's going north, so it's positive. All right, so now that we have all of that, we're trying to find the velocity of the red ball in the x and y direction so we can put it together and find the total velocity or the resultant. So let's look at our momentum equation. So we'd say the total momentum initially equals the total momentum final. Okay, initially is before the collision, so initially we have the momentum of the red ball initially plus the momentum of the yellow ball initially, and there should be an equal sign up above. The total momentum initially equals the total momentum final. So the total momentum is the momentum of all the objects, which would be the red ball and the yellow ball, is equal to the total momentum, so the momentum of the red ball final plus the momentum of the yellow ball final. Okay, and then we know our equation for momentum is m times v. So we can put that in. So now we have the mass of the red ball, the velocity of the red ball initially, plus the mass of the yellow ball, the velocity of the yellow ball initially, equals the same thing but final. Mass of the red, velocity of the red ball, final, plus mass of the yellow ball, velocity of the yellow ball, final. All right, now we're going to start dividing things into x and y components. So if we were to solve for, let's do the x component first, we could put little x components everywhere, and then we're trying to solve for the final velocity of the red ball. So that's this one over here. So maybe what I'll do is I'll rearrange the formula first, then I'll I'll make it all x components, and then I'll make it all y components. So let's solve for this VR final. VR final is equal to, so I'm just going to take all of this and move it to the other side of the equals. So I get MR VR initial plus M yellow V yellow initial minus mass of the yellow V yellow final. And I'm solving for VR, so I need to get rid of that mass of the red ball. Divide that out. Okay, so I'm going to do this in the x direction and then in the y direction. So I have VRX final equals mass of the red, V of the red x component initial plus mass of the yellow, V of the yellow x component initial minus mass of the yellow, V of the yellow in the x component final over the mass of the red ball. Okay, so mass of the red ball we said is just m. Velocity of the red ball initial in the x direction is this value here, 1.9. Plus mass of the yellow ball, also just m. Velocity of y in the x direction, this value here, negative 5.1. Minus mass of the yellow, still just m. Velocity of the y in the x direction. So now we're doing velocity of y in x direction final, so that's this one. And that's 0 all over the mass of the red, which is still just m. So this term goes away, and I get 1.9 m minus 5.1 m. Okay, I'm going to type this up. 1.9 minus 5.1, and I get negative 3.2 m on the top, and on the bottom I have m, so my m's cancel out, and I just get negative 3.2. So that's the velocity of the red ball in the x direction. Meters per second. So that means 3.2 meters per second. It's in the x direction, but it's negative, so it's going west. Okay. So let's do the same thing, but now with the y direction. So I have VRY final equals, so I'm using the same equation over here. I'm just changing everything to y's instead of x's. Mass of the red, velocity of the red ball, y initial, plus mass of the y, velocity of the y in the y direction, initial, minus mass of the y, velocity of the yellow ball, y direction, final, over mass of the red. Okay, so the masses are all just m's. Velocity of the red ball in the y direction is this over here. And the velocity of the yellow ball in the y direction initially is also 0. So both of these are 0. I'm just going to put them in right now. And then I have minus the mass of the yellow, which is still just m, and the velocity of the y in the y, so velocity of the yellow ball in the y direction, that's this value here, 1.34. All over the mass of the red, which is just m. So m times 0 is 0, m times 0 is 0, and negative m times 1.34 over m is just negative 1.34. Okay. So now I know the velocity of my red ball has an x component that's negative 3.2, so I'm going to draw that. It's going to the left or west. And then the y component is negative 1.34, so it's going south. Okay. So I'll put my numbers in. So I have 3.2 and 1.34. And now I'm trying to find my hypotenuse, which is my velocity of the red ball final. And I need to find this angle as well. So I'll solve for the angle first. Tan theta equals opposite over adjacent. Theta equals tan inverse of the opposite side, which is 1.34, over the adjacent side, which is 3.2. And I'll type that on my calculator. So I have tan inverse of 1.34 over 3.2. And that gives me 22.7 degrees. And now I'll also look for the magnitude of VR final with Pythagorean Theorem. So it's the square root of 3.2 squared plus 1.34 squared. And that gives me, I'm just going to type it up. 3.2 squared plus 1.34 squared, all in a square root sign. And I get 3.47 meters per second. So that means that the velocity of the red ball final after the collision is 3.47 meters per second at an angle of this direction. So the direction is west, and from west we're going 22.7 degrees towards south. Oops. Towards south. All right, and that's my question. So that was a really long one. Okay, last one we're going to do here is question 6. Okay, so in question 6 we have Jack who has a mass of 87.1 kilograms. So I'll just write that out. The mass of Jack is 87.1 kilograms, and Mary, so that's the mass of Mary, is 60.5 kilograms. They're running towards each other. They don't tell us which direction they're going, so let's just assume this is Jack, this is Mary. Jack is traveling, let's say, to the right, Mary is traveling to the left. Okay, so Jack is running at 1.3 meters per second, so I'll say positive is to the right, so the velocity of Jack, who's going to the right, is 1.3 meters per second. And Mary, who has to be going the opposite direction, so that would be velocity of Mary is a negative 5 meters per second. When they hit each other, they fall to the ground and they slide while attached to each other. Okay, if the coefficient of kinetic friction between the people and the ground is 0.3, how far did they slide? Okay, so first what we're going to do is just figure out what is their velocity when they collide, so after the collision. So these are their velocities before they collide, and we're going to find the velocity of the two of them, so Mary and Jack, who are now stuck together, final. That's what we're looking for. Okay, the velocity of their just one object, and what is their final velocity after the collision. So we're going to do the same as we did before. P total initial equals P total final. Oops. Okay, so momentum is mass times velocity, so I'm going to say mass of Jack times velocity of Jack initial plus mass of Mary, velocity of Mary initial, is equal to both of their masses together because they're now stuck together, so that would be an inelastic collision. Mass of mass of Mary plus mass of Jack. I'll put Jack first because I did before. Mass of Jack plus mass of Mary times their final velocity. So this is their velocity after the collision. And I didn't put subscripts because there's only one object now. They're stuck together. So it's Jack and Mary together. All right, so I'm trying to find this V final. So I'll rearrange the equation first. So I really just divided both sides out by this. And now I have the final velocity. So let's start to put in everything I know. Mass of Jack is 87.1. Velocity of Jack initial is 1.3 plus mass of Mary, which is 60.5 times velocity of Mary, which is -5, over both of their masses together. 87.1 plus 60.5. Okay, so I'm going to type this up onto my calculator. 87.1 times 1.3 plus 60.5 times -5. And then in the denominator, I have 87.1 plus 60.5. And I get -1.282317 meters per second. This isn't my final answer, so I'm giving lots of extra decimal places so that my answer is more accurate. Okay, so notice my velocity is negative, so that means that they are sliding to the left. Okay, so it now says, if the coefficient of kinetic friction between the people, Jack and Mary, and the ground is 0.3, how far did they slide? All right, so coefficient of friction. So now what we need to do is draw a free body diagram. Okay, so this free body diagram is of Jack and Mary. So I'll just write that out here. Jack and Mary. They're stuck together, so they're acting as though they're just one object. So what forces are acting on them? Well, there's always a force of gravity. And the force of gravity equals mg. And it's two people stuck together, so it's both of their masses. So it would be 87.1 plus 60.5 times g, which is 9.81. So let's just find out what that is. 87.1 plus 60.5 and times that by 9.81, which is 1447.956 newtons. Okay, what other forces are acting on them? Well, they're sliding across the floor, so they're on a surface. So there must be a normal force. So this is the normal force. And they're sliding because the velocity we got was negative, they're sliding to the left, okay? That's the direction that they're going. So if they're traveling to the left, then that must mean that the friction force is opposing their motion, it's going to the right. So this is the force of kinetic friction. And that's all the forces. So the force of gravity and the normal force are the only forces that have y components, and the object, the two people, are only moving in the x direction. So they're only moving left and right, they're not moving in the y direction at all. So those two forces, the normal and the force of gravity, those have to cancel each other out. So whatever we got for force of gravity, it has to equal the normal force. So it's 1447.956 newtons. So they're the same. And so now we can figure out the force of kinetic friction, which is the coefficient of kinetic friction times the normal force. So the normal force, which is what we just wrote down, times the coefficient, which is 0.3. So I'm just going to type those two on my calculator, and I get 434.3868 newtons. Okay, so now I have all my forces. So next, I want to find out how far did they slide. And I know initially what their speed was. Okay, this is their speed right here. So I want to say, okay, well, I need to find their acceleration so I know how far they slide before coming to a stop. And then I'll use kinematic equations. So I'm going to do F net equals ma. And I get to decide which direction I want the positive direction to be. Okay, so before I said to the right was positive, and I ended up getting a negative velocity, which means they're moving to the left. So they're moving to the left now, and now I can decide, okay, do I want to stick with the right being positive, or do I want the left to be positive? When I do F net equals ma, I like to make the direction they're actually moving be the positive direction. So in that case, I would say to the left is positive. Okay, so F net equals ma. Well, what are my forces? My F net is just Fk, the force of kinetic friction. That's the only force that's acting in the x direction, but it's a negative force because it's going to the right. So it'd be negative Fk is equal to ma. So I'm solving for A, which would be negative Fk over the mass. And this mass then is the mass of Jack and Mary. So I'll put that down just here. Jack and Mary. It's both of their masses added together. So negative Fk, my Fk is 434.3868 divided by both of their masses, which is 87.1 plus 60.5. Okay, so I'm going to type this on my calculator. And I get negative 2.943. Okay, well this makes sense. The acceleration is negative because we're slowing down, because friction is slowing us down. So now let's write down everything else we know so that we can use a kinematic equation to solve for how far did they slide. So I know my V initial, so this is their speed after they collide, which is this value over here. And it's negative because it's going to the left. But we just said over here that we want the left to be positive because that's the direction they're going. So I'm going to say V initial is the positive value now, since I said positive is to the left. So it's 1.282317 meters per second. The acceleration we just got up above, that's in meters per second squared. We want to know how far they travel before coming to a stop, so V final would be 0. And we're looking for delta S. Okay, so we need to find an equation that doesn't have delta T in it, because delta T is the one equation that we don't know and that we don't want to know. So we're going to use this equation, V final squared equals V initial squared plus 2A delta S. And we can solve for delta S, V final squared minus V initial squared over 2A. And we can sub in all of our values. So we have delta S equals V final, which is 0 squared, minus V initial, which is 1.282317 squared, over 2 times the acceleration, which is negative 2.943. And what do we get? Delta S is equal to I get 0.279 meters. That was a big question. All right, so that's my final answer there. I solve for delta S and that's it. So I get 0.279 meters. That's how far they slide. It doesn't say this explicitly, but it really means how far did they slide before coming to a stop. Because if they didn't come to a stop, they're still sliding. So how far did they slide means they eventually come to a stop. So that's why my V final was 0 over here. Okay, so that's question 6. Question 7, I want you to try it out on your own. It's a pretty challenging question. And then there's another video that's posted in the homework that you can take a look at so that you can complete it. Okay, thanks so much for watching. See you next time.